Now that we have learned about the architecture, let's see the major types of HA implementations. Hadoop supports two major HA implementations for storing metadata. One is quorum-based storage, and two is shared storage using NFS. You can see these in the slides. On the left, the quorum-based storage refers to the HA implementation that uses a Quorum Journal Manager, or QJM. During this implementation, the standby node keeps its state synchronized with the active node through a group of separate daemons called journal nodes. Daemons are long-running processes that typically start up with the system and listen for requests from the client processes. Each daemon runs in its own Java virtual machine, or JVM. When any namespace modification is performed by the active node, it durably logs a record of the modification to a majority of the journal nodes. The standby node reads the edits from the journal nodes and constantly watches for changes to the edit log. As the standby node seeds the edits, it applies them to its own namespace. In the event of a failure, the standby ensures that it has read all the edits from the journal nodes before it promotes itself to the active state. This ensures the namespace state is fully synchronized before a failover occurs. In shared storage using NFS implementation, the standby node keeps its state synchronized with the active node through an access to a directory on a shared storage device. Let's look at the HDFS name node component. The name node server is the core component of an HDFS cluster. There can be only one name node server in an entire cluster. Name node maintains and executes the file system namespace operations, such as opening, closing, and renaming of files and directories which are present within the HDFS file system. The namespace image and the edit log stores information of the data and the metadata. Name node also determines the linking of blocks to data nodes. Furthermore, the name node is a single point of failure. The data node is a multiple instance server. There can be n number of data node servers. The number depends on the type of network and the storage system. The data node server stores and maintains the data blocks. The name node server provisions the data blocks on the basis of the type of job submitted by the client. The data node also stores and retrieves the blocks when asked by clients or the name node. Furthermore, it reads and writes requests and performs block creation, deletion, and replication on instruction from the name node. Let's look at the Zookeeper component. Zookeeper allows distributed processes to coordinate with each other through a shared hierarchical namespace. The Zookeeper implementation is simple and replicated, which puts a premium on high performance, high availability, and a strictly ordered access. The servers that make up the Zookeeper service maintain an in-memory image of state, along with the transaction logs and snapshots in a persistent store. As long as a majority of the servers are available, the Zookeeper service will be available. So let's look at how automatic HDFS failover relies on Zookeeper. It does so with the following things. One is failure detection. Each of the name node machines in the cluster maintains a persistent session in Zookeeper. If the machine crashes, the Zookeeper session will expire, notifying the other name node that a failover should be triggered. And two, active name node election. Zookeeper provides a simple mechanism to exclusively elect a single node as the new active node. If the current active name node crashes, another node may take a special exclusive lock in Zookeeper, indicating that it should become the next active name node.